Dear learners, welcome to week 6, lecture 1, development of approximate solutions for finite cell subjected to arbitrary support conditions. In the previous lecture, I have presented the solution for a infinite shell and finite cell subjected to the simply supported boundary conditions. But as you know that these are very simplified form, it is not always possible that we are having only simply supported boundary conditions. So, that if a panel is subjected to clamped, free or any combination of boundary condition, can we get the solutions? Yes, we can get the solutions, and these solutions comes under the, if it is analytical solution, comes under the approximate solution, and there is a purely numerical solutions, like you can say finite element solutions. In this techniques, basically first two, these are the approximate techniques. That Ridge method and Galerkin method is very popular if we are interested to develop a solution subjected to arbitrary support conditions. And the third one is the extended Kantorovich method. Though this method was first proposed in 1939 by L.V. Kantorovich and Krylov in a book of higher engineering mathematics, which was initially published in Russian language, and in 1968 or 1964 this book was published in English. Here that Professor Kantorovich and Krylov try to further improve this method, and later on this method is known as Kantorovich method. Basically they try to improve the Ridge method or Galerkin method. So, I would like to briefly explain what is the limitation of Ridge or Galerkin method. In Ridge or Galerkin method, the function we choose, let us say if we are going to solve a plate or a shell, and if we take a variable, let us say in present case we say a variable is a function of x and theta. So, we can express this variable, let n is equal to 1 to you say infinity or any number, let us m or n, then maybe we can say that C I j is any constant and phi I j may be function x and theta. So, here this function phi I j need to satisfy the essential boundary conditions. Essential means the kinematic boundary condition, displacement boundary condition it should satisfy. If I say that the shell is simply supported or shell is clamped or shell is free, so this phi I j should satisfy those boundary condition. Then we can substitute into the weak form and try to solve. So, ultimately this Ridge and Galerkin equation leads to a algebraic equation like R x is equal to C. So, very first limitation is that it is very difficult to find out a function which satisfy the other boundary condition easily. If you say that clamped or free and so on. Then if we are not able to find out that function, it is approximate function, then the convergence issue will be there, that result will not converge. So, to avoid this, basically they depend upon the initial choice. If initial choice is very close, then we will get the result. If initial choice is far away, then we will not get the accurate results. So, to eliminate this dependence, Kantorovich in 1939 proposed a technique that we can express this into a, let us say, x is a function of x and y is a function of theta, basically in a bivariate system. Initially it was a single term that x is a function of x only and y is a function of theta. And if we substitute into a weak form, then it reduces to a differential equation. Let us say if we assume first, we know that if we are assuming a solution along theta direction and interested to solve along x direction, so a will be some constant a dash x is equal to 0. So, it is lead to a ordinary differential equation in x direction. So, this differential equation is solved exactly and then, so basically subjecting to the boundary condition. In this way that assumptions along x direction, that solution is not dependent on x direction, it is only dependent on one direction. Previous case, the initial gas dependent on both x and theta. But in 1968, A.D. Kare, Arnold Kare developed, means further extended this Kantorovich method. Basically from 1939 to 68 it is known as a Kantorovich method, and this method is briefly described in, I think, most of the book that is based on energy methods. One can see, you will find it is devoted half an page or 1 page. But in 1968 K.D. Kare extended this method and it is known as extended Kantorovich. So, what was the approach in that? Let us say we assume first in y direction and going to solve for x. He say that in the next step we are taking x is assumed, let us say now it is becoming second choice, x is assumed and we are going to solve for y1, solution for y1. So, in the first case, in the 0 step, y theta is assumed, but when we are saying that x1 is known now as per the boundary condition, actual boundary condition, and this is taken as now assumed gas and y theta is solved. So, we can apply the different support condition and y theta is subjected to actual boundary condition which is there. So, in this way, next now y1 is known and x2 is solved. So, in this way it process is iterated, that once one is known, solving for other. So, this x and theta ultimately gives you the two set of differential equation. One, let us say coefficient A, x dash of, x dash means x comma x is equal to 0 if static or some loading, and then b times of y theta comma theta, let us say q. So, there will be two set of ordinary differential equation. So, when y is known, this equation is used. When x is known, after this y theta is solved. So, in this, using this iterative procedure, we can find out a accurate solution subjected to the various boundary condition. So, first he presented for the case of a plate, and then this method has been extended to beams, shell, bending, free vibration, buckling, all kind of this thing. And recently, I think in 2011 and 12, Professor Kapuria and myself developed this method to 3-dimensional case, and we are still, our group of students are working, and recently we have developed a solution for cylindrical shell, 3-dimensional cylindrical shell subjected to arbitrary support conditions. In this lecture, I will explain that how to develop a solution using the extended Kantorovich method for a cylindrical shell panel. So, in ridge method, it is a very recent article that nonlinear vibration analysis of a laminated composite angle ply cylindrical conical shells. So, in this paper, that approach of ridge method is presented, results are presented. So, interested learners can go, means how to apply the ridge method for the present case, can go through this paper. In the next, I have briefly only in this slide the papers related to shell is compiled here. So, the paper was, this is buckling analysis of symmetrically laminated composite plate. So, and then the cylindrical panels using the extended Kantorovich, bending analysis of a symmetrical laminated cylindrical panels using extended Kantorovich method. Then the sector plates, then again so different pavements and the clamped cylindrical panels, then thick sector plates. So, basically which are having some curvature, and the title is that semi-analytical solution for a thick laminated cylindrical panel with various boundary condition. So, in the present lecture, I shall explain the state of art presented in this paper, so that learners have an idea that how to move ahead or how to use this method for developing a solution for a cylindrical panel using first order shear deformation theory. Then the free vibration analysis of a cylindrical panel is done, then moderately functionally graded shell panels, and then spherical shell panels, and then the conical shell panels. So, all kind of different variety of shell panels are studied using the extended Kantorovich method. And then the recently, I think in 2016, that professor from Iran developed a layer wise theory, cylindrical shell panels. So, I will discuss that paper in detail. So, first of all, that here a finite shell is considered for a study. In that, the displacement field in this paper is assumed like this: u naught plus z times of beta x. Instead of a psi 1 psi 2, in that paper it is used at beta x and beta theta. Then the concept remains same, x, theta and z, and the mean radius r. These are the strain components. The major difference is that here the name is slightly different and they have made a component like this: epsilon x x 0, epsilon x x 1, epsilon theta 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 1, and in gamma x theta is divided into w x theta, w theta, and like that mu x mu theta. But in the previous lecture L3, the finite shell panel, the terms are same, only their notation is slightly different. Instead of a psi 1, they have used beta x, instead of a psi 2, they used beta theta. One first difference is this, and the second difference is this notation, that what is w theta 1, the w x 0. So, ultimately this is nothing but v 0 comma x and 1 by u comma theta. So, they have written like this in a short form instead of this. So, this is our strain displacement relations, and this is our 5 set of governing differential equations, which is same, but for the present case there is no in plane loading along x direction, no theta direction, only transverse loading is explained. These are the boundary conditions, means the variable need to specify that x 0 and x a and theta 0 and theta psi. Stress resultant similarly defined as we defined in the previous case. Now, ultimately this cell constitutive relation is presented like this, that nx, nx theta, qx, n theta, n theta x, q theta, mx, m theta. So, they are arranged in a matrix form, and these are the coefficients of a matrix, and these are the strains components. So, these are the different components they have arranged such that we are getting a matrix like this. The various terms here you see that G11, G66, A12, A66. Similarly, like in we have defined F1, F2, F6. So, they have just name it G11, G66. So, they are same as that Aij plus 1 by R Bij. So, Aij is constant times dz and Bij is z times of nqij and so on. So, these are the coefficients. Now, the question come up there that these the basic governing equations. Now, for the arbitrary support conditions, first we will define the variables which need to be specified for a particular boundary conditions. For clamped case, for clamped case u0 need to be 0, चाहे आपकी वो कोई भी एज हो, all edges, all displacement and all rotations, beta x and beta y on all edges. All edges means you may say that x is equal to 0 and a and theta is equal to 0 and here they have taken alpha. If panel is subjected to simply supported boundary conditions, it is very important to understand that there will be difference if it is simply. If it is edge is 0 and a, then we need to specify nxx is 0, v 0, w 0 and moment and rotation. The theta 0 and alpha, u 0, n theta 0, w 0, then m theta theta 0 and beta x is 0. If it is free, because we have to choose only those combination x 0 and a, तो आपके सारे stresses nxx, nx theta, then x 0 and a, qx, mxx, all stress resultant is going to be 0 if edge is free. If other as along circumferential direction, theta is 0 and alpha. So, for that case it will be n theta theta and theta x, q theta, m theta theta and m theta x. Here it is a cylindrical shell. So, n theta x not equal to nx theta. Same way m theta x not equal to mx theta. Now, you see for the case of clamped case, all essential variables are 0, means the kinematic boundary conditions, all displacement and rotations are 0. So, for the case if we are interested to develop a Ritz solution, then all round clamped solution can be developed very easily, because we can find out a function in which all variables are 0. But if a panel is subjected to, like let us say x is equal to 0 and a, it is simply supported, and theta alpha it may have free or something, then it is a mixed boundaries. You have to specify nxx, v naught and w naught. So, there are different type of formulations, even for the case of free, all stress resultant need to be specified. So, boundaries are mixed, then we may at some edge we may specify the displacement, at some edge we may specify the stress resultants or moment resultants. For such cases, the formulation can be done in two different ways. Number one, that we have all 5 partial differential equation that we called a governing equation of shell. So, if we substituting the use of cell constitutive relations, we can express in terms of displacements variables and their derivatives basically. In the case of simply supported, we did it. They will be expressed only in these 5 variables. Then the boundary conditions, like if you say that mxx need to be 0, or if you say that m theta theta need to be 0 or n theta theta need to be 0. In that case, for getting the boundary condition, we have to first convert into using the cell constitutive relations, convert into that form. Let us say a11 and some u comma x plus, I am just assuming it, a12 some v comma theta and so on. So, we are going to satisfy the boundary condition in this sense, because n theta theta is not our variable that time, and these governing equations may be 4th order, sometimes higher order, 8th order and so on. Second is that using the cell constitutive relations, and 5 PD, we make set up in such a way that we are assuming stress resultant as a variable also, like nxx, n theta theta are our variables. Then we can directly specify because that is our variable. So, but we have to use the cell constitutive equations in the governing part. So, in this paper, the second approach is used where u naught, v naught, w naught, beta x, beta y, nx, nx theta, n theta, n theta x, mx, mx theta, m theta and m theta x, qx and q theta. So, number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 and 15. So, we have a 15 unknowns. Previously, if we go for a displacement, we have only 5 unknowns. Now, we have assumed that stress resultants are also unknowns. So, we need 15 governing equations. So, we have 5 PD partial differential equation which we are using every time, and 10 your cell constitutive relations. So, in this way we will get a 15 governing equations, 15 variables. Yes, definitely we can sort it out. Now, you check the boundary conditions. So, at an edge we can provide 5 at particular edge if we solve in one direction and second in another edge 10. So, in one direction maximum we can solve 10 variables in one direction, in any one direction, whether you talk about along x axis or whether you talk about along theta axis 0 and alpha. So, you have a 10. So, out of these 15, we used to select in such a way the variables for a particular set along those boundary condition, they will be the primary variables, and rest of 5 variables will be expressed in terms of these 10 primary variables. Similarly, if we solve along theta direction, then we assume the reverse way, that variables which comes along theta direction considered as a primary variables, and other variables can be expressed in terms of primary variables. So, in this way definitely these 5 is fixed, but out of these 10 we have to take another 5. So, based on this, that for example, if somebody asks me to choose, then I will say these 5 variables along x is equal to 0 and a I am going to solve. So, I will take as a primary variable these 5 and plus 5 displacement variables. Similarly, along the theta I will take these 5 variables. Then how do we proceed for the case of Kantorovich method? So, this u, let us say u I have given one variable. So, this x is a state variable and I means 1, 2, 3, 4, 5, I will go 1 to 15. xi, 1 means u0, 2 means v0, 3 and so on. It can be expressed that any variable xi I which is a function of x and any variable psi I which is a function of theta in a bivariate form. Xi एक वेरिएबल है which is only a function of x direction, and psi I is another variable which is only a function of theta direction. It is similar, like if you remember that in a double Fourier series, in previously we said that sin m bar x into sin n bar theta, where this is solely a function of x and this is solely a function of y. But this type of combination is possible only for simply supported case. Now, we have taken a general function. It may be sin or it may be something else. Next, that in this paper we have chosen the variable like this x15 and xi and psi 15. Now, substituting these variable into 15 governing equations and applying the Galerkin technique, because all these are in the form of PD or OD. So, we have to find out in terms of a weak form. So, applying the concept of Galerkin, ultimately it reduces to a set of, let us say S, a matrix, and xi, and this is the loading vector. Algebraic differential equation along the xi direction. Similarly, we will get another set of equation v into psi, and let us say for loading vector it is w. This is also a algebraic differential equation and that can be solved. This is one of the way that we can convert into a weak form, and then using the concept of Kantorovich method we will get a two set of differential equation, one which is a solely a function of x and another. Here the S, the most important part. Here S is nothing but it contains all the components. Let us say S16, there it shows one component I16 into D, where I16 is nothing but it is phi I, phi j, d theta 0 to alpha, if we convert into a weak form. So, ultimately because we initially we know phi j along theta direction, so we have chosen any function and converting using the concept of weighted residual method, it is known as weighted residual method. So, through that our concept of, let us say, complete n, complete a and some epsilon. So, that can be converted into a weak form, integrated form, let nx dx and some, if I am writing just a constant and something. So, from there along the theta direction psi is known to us, so we can take as a constant, and the variables which is having the derivative along theta will be considered in that governing equation. Same way, when along x direction is known, then we can find out along the theta direction derivatives. So, this method has been applied and it is found that initial choice of a function does not matter. Means, if you say that initial choice may satisfy the boundary condition, may not, but that solution will converge fast. It is not like a ridge that it's mandatory satisfy, because through the iterative procedure we can satisfy the boundary conditions and ultimately we get the final result. So, these techniques are developed in recently, has applied for a buckling of a shell or a non-linear vibration of a shell or the carbon nanotubes, composites and so on. So, this is very I would like to say that efficient method. One can try, one can go for the solution. It need to be developed further for a special cases, and this method has recently even tried for skew plates and plate with having some cutouts and so on. So, later on this method has been developed. Now, the concept of pure numerical techniques like your finite element solutions. So, if you these days you will find that in literature, if you go for a cylindrical shell, then you will find lot of research articles, around 22,000 articles are shown in the Scopus, and there you can see that number of works has been published using the finite element techniques, using the Ritz technique, using other techniques. So, even very general cases or general loading conditions, pure numerical techniques can be applied. So, methods have been developed. But for the cases, if you are interested for approximate or analytical solutions, the advantage of analytical solutions over the numerical technique is that if the boundary effects can be accurately predicted by the analytical solutions, and the parametric studies can be done by easily by the analytical techniques, and these are somewhat closed form formulas. So, one can easily do the parametric studies, optimization and so on. But if you go for pure numerical techniques, the boundary effects cannot be captured. What do you mean by the boundary effects? The effect means when it is simply supported, then there is no effect of the boundaries, but when it is clamped or free. So, let us say I just would like to explain with the help of a cantilever beam. If a cantilever beam is subjected to such kind of a loading, so at the free edge, so over this edge nxx need to be 0 because this is free, and moment need to be 0. So, if you want to see the variation, then it may be some having moment. So, near the boundary it is just dipping, making some effect, it is not smoothly going there. So, in the case of a composite plate, because of it is more prone, in isotropic it is not, but when you talking about a layered composite plate or a composite shell, so because at each layer the material property is different and they causes a sharp variation of stresses, shooting variations, either they are increasing or decreasing very sharply. So, due to the delamination occurs. And in the composites, this is the most prominent problem that we are trying to overcome, or we are to understand that how much, what level of stresses are shooting in this area. So, if this edge is free, then it is that at the very edge stress need to be 0, but just near the edge it is very high. So, we are interested to find out that which causes the delamination in the composite cells. So, for that kind of accuracy we need analytical solutions the best. So, these days a special purpose finite element is developed, or that the concept of numerical techniques plus analytical techniques are combined together, that is known as sometimes a very famous technique SS DQM, means state space and differential quadrature method. These days another method is DQM, differential quadrature method, that is most very popular. If you go through a recent research article, you will find that in the case of shells, I think lot of paper are presented using the DQM approach, and 2 books specifically from that Italy have been published using this approach, that solution of a shell using the DQM approach, differential quadrature method. In that basically the differentiation means derivative is presented in a form of a series. Like we want to solve a like u comma theta theta. So, u is our variable. So, can we express this variable in terms of a linear series in some functions, so that solving a differential equation first order, fourth order is typical. If we can convert into a algebraic form by somehow, that is easy. So, with the help of DQM, that these derivatives are converted in terms of some algebraic form, so that we can get the solution. So, with this I end this lecture. Thank you very much.